Hello, today's presentation about nanoscale and ultra-fast thermal imaging of gallium nitride RF devices. And I'm working with my colleague, Professor Peter Aaen from Colorado School of Mines. And we are going to discuss about some of the recent applications of thermal imaging.
And so like any good presentation, a lot of this material has been developed by many of our colleagues. So I just want to mention Dr. Christian Mattei, Dr. Haraswatsi, Dr. Jonas Urbanos, who's taken a lot of these measurements throughout their PhD dissertations. And also we can't forget Dustin Kendig, who works for Microsanj. Okay, so as we look at thermal measurements, what we can see in RF and microwave circuits is that the density of these circuits is increasing. That could either be the spacing between the area that the circuit takes up or the power density. In either case, what we do is we get increased heating, and this obviously impacts the reliability and the lifetime of the devices. And the electrical performance, we all know, is also impacted by thermal effects. And what my team has been doing a lot over the past 10 years is looking at how do we go ahead and develop simulation and measurement techniques for a coupled electrothermal optimization. So we want to be looking at how the temperature impacts the electrical performance and how we can go ahead and design the chips to take this into account. And this is really a complicated coupled behavior, because what we'll see is that if we change the chip slightly or how we feed it, we can get very different temperature distributions. So on the bottom here, you'll see some thermal scans for an LDMOS device, a silicon device, where we have two different temperature profiles for the same layout, just different feeding of the transistor. And whether it's small changes to the input matching network or harmonics terminations as you design your amplifier, you can get very different temperature distributions. And this is critical for us to take into account in the design and optimization of the transistor.
So here is an example where an IR thermography, which is a standard, is compared with transient CCD. IR has the highest sensitivity, can go down to microkelvin with lock-in detection. But the real challenge is that gallium nitride is transparent to IR. Metals have low emissivity. So as a result, the spatial resolution is limited and time resolution is limited. So as you can see on the top figure, you can see the overall heating. But when we look at CCD-based thermoreflectance, we are able to see heating in individual gate areas. So one of the early methods that was applied for temperature measurement is Raman thermometry, and the top left-hand side shows the configuration. A laser, in this case, a green light, is focused on the sample, and in the reflected light, we measure a small Raman shift. That is what is shown in the bottom left-hand side. These tiny shifts correspond to specific covalent bond vibrations, such as gallium nitride E2 or A1 vibration. And what is interesting is that the position of these peaks and amplitude of them can be used to measure temperature. A beautiful example of this is shown on the top right-hand side, early measurement by Kubal's group that shows temperature down to a silicon carbide substrate at the depth of a couple of 100 micron, up to the top surface, the gallium nitride. So you can really see the thermal boundary resistance. While this is accurate, if we could press next, there is a real challenge is that the peaks in the Raman also are affected by the stress, such as inverse piezoelectric. So detailed calibration and sometimes modeling is needed to get the accurate temperature measurement. The other component of Raman is the point measurement. Really, it takes quite a bit of time to do an image by scanning it. But the advantage of 3D is valuable to look at the substrate effects. The next view graph shows a thermoreflectance measurement system. I briefly discussed. The idea is that the same optical microscope that you use to visualize your sample, with the right synchronization with the light source and the device, can be used to measure very slight changes in thermoreflectance and give us a sensitivity of 10⁻⁵ in reflection, which corresponds to a temperature sensitivity in tens of millikelvin.
And so this is a system here on the left that was installed in my former laboratory at the University of Surrey before I joined the Colorado School of Mines. And you'll see the installation here where we have this on a table showing the imaging of a 74 gigahertz device that I'll show some measurements on in just a few slides. So this is one of those devices. This is a zoomed out view of a multi-stage 74 gigahertz gas p-hemp amplifier. And what we did was we went ahead and biased this, and then we can start to look at the individual, each one of the individual cells. And what we can do now is, if this is with a 5x CCD image, we can now go look at its pulse performance at the finger level. And this is where we're going to get to see a lot of the really detailed heating. So at 100x magnification, we can view just a few of the fingers, and I'll play a movie here. We're able to go ahead and capture frame by frame with the measurement system. And what we can start to see now is how the device heats up over time. And what you'll see the location of the heating. And if we go ahead and look at this on a frame by frame basis, you can actually see when the fingers are heating themselves, the self-heating from each one of the fingers. And then you can start to see as the heat goes ahead and combines, and you get the mutual heating between them all. This is a really pretty image, but what we can do now is we can start to do a lot of data manipulation on this so that we can see where the local time constants are for all the heating. And that's what we can look here. Is what we can do now with the Microsanj system is we can go ahead and determine areas of interest where we want to see the temperature. And you'll see in the bottom left-hand corner here, we have 3 areas. You can define these areas. They could be individual pixels, or you could have area, or you could look at all the pixels simultaneously. And what we're able to do in this spots now is to pick out the overall temperature within that area of interest. And at the top of the screen here, you'll see how the temperature rises differently depending where you are on the device. So here you'll see very different delta T's, whether you're on the gate, the drain, or the source of the transistor. And then, from the delta T change and the time, you'll see the time axis there, we can go ahead and pick out the thermal time constants. And so what we're starting to see now, usually we'll measure and try to pick out an RC time constant for the entire chip. But here what we're starting to see is there's differences depending where you are on the chip. So as you start to develop a full electrothermal model for the entire transistor, these are some things that you might want to take into account for an overall distributed thermal model. And with the Microsanj system, this is something that we can go ahead and then verify that overall model. So we're going to move a little bit now into talking about gallium nitride power transistors. And here we have a device that we bought. It's a GaN on silicon carbide from Cree. It's a 20-finger device with 25 watts. It's a 30-watt saturated power designed to operate at 28 volts with an IDQ of 250 milliamps. And here what you can see now is a cross-section. This is from one of the Cree application notes where we expect the high temperature just on the edge of the gate nearest to the drain is. Now, in these devices, there's often a field plate. So when we're looking from the top down, you can't necessarily see that exact spot, but with the resolution of the Microsanj system, we can get right into right in between the gate and the drain, and we can start to see from the top where that heat originates from.
So what you see here is one of the recent results published over the last year about cross-sectional thermal imaging of a gallium nitride and silicon carbide HEMT. So it required delicate device preparation. The top image show the CCD. You can clearly see the source, drain, and the gate, the gallium nitride layer, and the silicon carbide. With the same optical imaging that you visualize it by now locking and looking at different powers and different delays on the bottom, you can see at 2 microsecond delay on B and 10 microsecond delay, what is the temperature profile. The top row is at the power dissipation of 3.3 watt per millimeter, and the bottom row is about 5.8 watt per millimeter. And what you can see is, for the first time, we can actually see the heating underneath the gate, and we can see how the heating scales with time. The time constant is one of the things was emphasized earlier, but also you can see how the biasing affects this. So this was quite powerful. In the next view graph, what the group has done is they look at the impact of what happens in different layers. First of all, on the left-hand side, you see the transient temperature at 2 locations, gate and the gallium nitride. And here is important because all top measurements always measure the gate. And what you can see, the gallium nitride get hotter at the beginning as expected, because that's a source of heat. It has a faster time constant, but eventually after a certain time, 10 microsecond, equilibrates. So you can see the time constant being different. So that's quite powerful, and that's quite important for validation. And what you can see on the right-hand side, the same power is applied in the 3 cases, A, B, and C on the right-hand side. The same power of 3.3 watt per millimeter, but you can see that the V-gate source goes from 0 to minus 1.5 to minus 2.5. So basically, you can see as you go to the pinch-off how the distribution of heat changes. And again, have been quite a bit of modeling work, and this is one of the first time we can visually see what happens in this type of device. So that was one of the recent validations. And next, what I want to describe is how the theory and experiment work. That's a slightly different paper by another group from Penn State. In this case, you can see the modeling result right now. So first of all, where is the Joule heating happening in the pinch-off region? In this case, 2.5 watt per millimeter. And you can see when you are in the left-hand side, pinch-off, all of the heating is near the drain. And when it's on the right-hand side, is more distributed. Theoretically, you would expect, even though the power is the same, the left-hand side give you a delta T max of 38 degrees, while the right-hand side is 28 degrees. So that's an important point. That means that thermal resistance is bias dependent. Next, what you have is the actual experimental results that was obtained. This is using visible, and you can see the accuracy, 38 plus minus 0.7 and 28 plus minus 0.9. So is quite accurate, and this is one of the first time we could really see theory and experiment matching, so it's a validation of the theory. But what is interesting is that this is still on the metal side. This is not on the submicron scale. In this paper, they really wanted to understand what happened inside the transistor. In the next view graph, what they used is a comparison of the Fourier model with a Boltzmann, which is basically subcontinuum. And what you see here is temperature profile from drain on the left to source on the right. So kind of pay attention, things are reversed comparing to past, but the Fourier law is the dashed blue line, and you can see at the power of 250 milliwatt, the hottest point is about 45 degrees or so, and at 500 milliwatt, the hottest point is close to 100 degrees. But that's what Fourier predicts. Now the Boltzmann average with some sort of subcontinuum and a mean free path, which is given here by numbers 84 nanometer or 400 nanometer, predict heating that go up to about 120 degrees. And you can see there's a difference between Fourier and non-Fourier is substantial. 20 degrees, it's factor of 4 in lifetime easily. So that's quite important. And if you click next, you see a data point here that was obtained by UV transient thermoreflectance imaging. The advantage of UV when you go to 365 nanometers, you have a signal on gallium nitride near the top surface, and you can see that matches quite well the subcontinuum and is much hotter than the continuum. And this was a paper that they really emphasize the importance. What creates degradation is often not highest temperature, but temperature gradients. So knowing in this case what happens under the gate between distances of 1.5 to 5 micron is quite important, and it also shows the advantage. And one of the comments the paper had is that if you use Raman for the same device, you can also get a result in gallium nitride, but is volume average over a region of a few microns, so you cannot really get the peak temperature. So this is another advantage of this technique.
So one of the things we were really interested to see is to see how these devices, we could measure them in a load pull system. And so what you're showing here is some work where there's an impedance transformer designed with a TRL calibration, and what you can see on the bottom of the image is where the gallium nitride device and its package is inserted into the system. And what we do for measurements is we'll remove the lid so that we can go ahead and then see down on the gallium nitride device itself and then do the thermal reflectance measurements. So as I'll show here shortly, this is going to be embedded in an NVNA load pull system, and then we'll do measurements, and we can either take those at the connector plane or through the TRL de-embedding, get right down to the edge of the packages. And that's what you're looking at here. This is a schematic of the overall system. So with the, you'll see at the bottom, this is the thermal stage here with the lens from the Microsanj system. And here we have, the system has a 50 nanosecond temporal resolution. So this is an incredibly fast imaging. We can actually see the transient heat evolve as we do the measurement. And it's embedded into a load pull system where we have a source and load tuners with couplers just before the transistor test fixture. And then this is all connected to a PNAX. And the system that we built and designed has a capability up to 18 gigahertz, half kilowatt pulsed, and doing this all in an NVNA style measurement so that we can get not only the fundamentals, but the harmonics as well. An image of the full integrated system is here. You'll see the source and load tuners that you can identify on either side of the image. And then the thermal stage of the Microsanj system is right in the middle. And that's all connected then to an AMCAD pulse IV system so that we can pulse on and off the device. And then the PNAX is behind the microscope that's above the thermal stage. And then the rest of the electronics for the thermal reflectance system are on the right-hand side. So this whole system then allows us to do the measurements that we're going to show here in just a moment. So one of the things that we did was first we zoomed in on a finger and we wanted to see where the heat was being generated. And so you'll see on the right-hand side the image of one of the fingers where we're going to zoom in. And then in the bottom left-hand corner, what you'll see is along the top finger, that's the gate. And you'll see, just as predicted by the simulations that Ali showed earlier, you can see that the heat is being generated right at the edge of that gate. And so this was a steady state measurement where we biased the device and we looked to see what the temperature would be under steady state conditions. And then we went ahead and started to look at specific measurements. So here we're looking at we've tuned the fundamental for at the load for maximum output power. We didn't have a harmonic tuning capability, so we probably could have gotten a little bit better in the drain efficiency had we had that, but still what we were interested here to see how the device behaves under steady state conditions. And as we look at each one of the individual fingers, so we have the nice image from above. This is we're calibrating now on the gallium and measuring on the gallium nitride. So this is the top layer of the device is translucent. We get right down to the GaN and the temperature right at the 2 deg. And what you'll see here is a graph on the bottom where we've numbered each one of the individual fingers. And what you can see is the temperature distribution across the device. And you'll see that it's pretty constant across the overall device, indicating that it's a pretty well, all the fingers are well spaced out, and under transient, these steady state conditions, everything behaves kind of as we would expect. As we get into the transient measurements, what we're going to do now is the device, we're going to measure it with that 50 nanosecond resolution. And in the bottom image that I'm showing here, this is a movie as we heat up the device. And what you'll see now, if you watch the movie on the top where we do a cross section, you'll see that some of the fingers do actually heat up a little bit asymmetric. And that's something that if you're going to design for memory effects, each one of those transistor fingers has a slightly different thermal environment than even though they're all laid out identical, the fingers themselves, due to their local environment, are slightly different. So there's an asymmetry here that you might want to take into account, and you only really see this under these transient imaging conditions. And in this measurement, we're measuring for the first 200 microseconds in 10 microsecond steps. And finally, we wanted to present some of the latest work where we were looking at using gallium nitride devices, but in this case, using them in power conversion applications. And here, Christian Mattei designed, using the same GaN hemp device, used the device as a switching transistor. And the idea here was to create a 20 to 40 volt DC-DC boost converter. And he was able to, find an example of this in the literature, reconstruct and design this device. And then we went ahead and implemented this inside of, with the thermal stage that I'm showing in the image above, the CCD camera, connecting an oscilloscope and a power supply. And here the idea is to be able to go ahead and measure the temperature on each one of the fingers as the device switches. And so that's what I'm going to show on the next page here. What we did in the first case, in the upper right-hand corner, we went ahead and we calculated, this is at a few megahertz. Under Class A bias conditions, you can see in the top graph the drain current and the drain voltage. And if we multiply those two together, this is really the dissipated power. And that's what we're seeing in the red curve, right, in the red area. And we assembled a full model of this, a thermal model. And so it's an electrothermal model where we take the power dissipated by the transistor fingers, and then we go ahead and combine that with the thermal model inside of ES. We do a electrothermal simulation. And what we can see now is that the measurement from the Microsanj system is giving us the exact same dynamic temperature that we're seeing in the simulation. So this is pretty fantastic, because as we have an amplifier here, what we're measuring now in most measurement systems, what you'll measure is the average temperature. Here, what we're doing at 1 megahertz and later at 5 megahertz is a measurement where we're actually seeing the dynamic overlap between the I and V curves in the transistor itself. And so going back then to the boost converter, what Christian Mattei did was he looked at the design of it, and you'll see the drain current versus drain voltage, so that we can see the device as it's switching on and off. And from that, we can calculate then the dissipated power. And that's the image in the bottom left-hand corner, where you'll see the drain power dissipation under two different conditions, under 1 megahertz switching and 5 megahertz switching. And what we can do then is we can go ahead and take the full die. So we have a model now for the full die, the electrothermal, the one that we used above in the Class A. But now we're using it, the same model under switching conditions in the boost converter. And what you're seeing here for the first time for one of these boost converters is a prediction. You'll see the simulations in the dashed black lines in the bottom right-hand corner versus the measurements that are shown in the colored lines of the temperature or the dynamic IV overlap at the drain. So that's creating the dissipated power for each one of the individual fingers in the transistor. And now we can detect and see how that temperature changes as the device switches on and off. So we're peering into the device and seeing how the temperature operates. And if you're designing a boost converter, rather than looking at what is traditionally done, the average temperature, here we're able to look at the overall instantaneous temperature within the device as it's operating. So that was some of our latest work, and it's pretty fantastic to see, one, the resolution of the system, and two, the accuracy that we're getting compared to the models. So with that, Ellie, I'll leave this to you to maybe start some summary comments.
Thank you, Peter. These are outstanding results. One should pay attention not only the time scale, but the temperature changes that happen on the order of a few degrees within a few microseconds. And of course, when theory and experiment match, this is a good indication that we have good understanding where power dissipation happened, but also where are some of the thermal properties of the materials. And I think, as we push the devices to higher speeds and higher powers, the feature sizes of devices are submicron. So we really need advanced techniques to be able to characterize, calibrate the models. For example, there is a big push on the gallium nitride devices for more advanced substrate or interface layers. And there's always unknowns. When you measure a total thermal resistance, where it's coming from, there could be multiple factors. And the transient temperature profile is almost like a radar. It tells you where the heat goes, and we can use that to better model different layers, as was shown earlier. So hopefully this examples here shows the potential of full imaging that is high speed and high resolution, spatial resolution. Of course, there is always potential to do complementary measurement using Raman or IR. And we look forward to hear more from industry partners. What are the areas where we need to push the limits of these techniques? What are the areas of device applications where the coupled electrothermal analysis could be beneficial? So we look forward to hear from our industry partners some of the inputs they have. Thanks for your attention. Thanks, Peter, also for your time.
Thank you, Ellie.